Welcome. Let me say something about Poincare-Hopf, which can be seen as a Gauss-Bonnet theorem where the curvature is just integer valued, where the curvature is a divisor. So here's the framework. It works for graphs, it works for finite abstract simplicity complexes or delta sets. You just push the energy, this total energy is Euler characteristic, from the simplices to vertices or to any other part of space which you want to have. So the most common thing is that you push it to the lowest dimensional parts, which are points, and then you get these indices. And these indices are integers, and you add up all these integers, you of course have still the Euler characteristic. But these indices are in general then just on very few points. Like in classically, when you have a setup where the energies are distributed to the critical points, then you have only a few critical points of a function in general. Now, unlike Gauss-Bonnet, this is Gauss-Bonnet Chern. Gauss-Bonnet Chern, you taps into the Riemann curvature tensor, which is a complicated beast. The indices are much simpler. They are integers, and they align when you approximate a manifold by a discrete manifold. So you can do that always using Nash's embedding theorem. A Riemannian manifold can be embedded. You can produce a probability space of functions and so get indices, and to take the average, you get the curvature, you get this Gauss-Bonnet Chern curvature. So that's the link between the discrete and the continuum. Now, what happens is we have looked at the second order curvature last time, and of course also the second order curvature can be seen as index expectation of Poincare-Hopf indices. What you have just to do, you have to do also two steps when you do produce the indices. So first of all, you push the energy to the highest dimensional parts of space, which are the facets, and then you push it back to the vertices or wherever you want to have it. And then you get, by averaging, you get the curvature which we have looked at. We were especially interested in the two-dimensional case because of sectional curvature. So why are we interested in sectional curvature? Of course, because sectional curvature comes in when you define positive curvature manifolds. And there is an important open problem of Hopf, asking whether if you have a positive curvature manifold which is even dimensional, whether the Euler characteristic is positive. Now the difficulty is if you take the sectional curvature, what happens if you take sectional curvatures, you can attach you have a geodesic sheet, you have a point and you have a two-dimensional direction. This gives you a geodesic sheet, and this Euler characteristic of this geodesic sheet is of course the integral of the curvatures, and these curvatures, two-dimensional curvatures, are the sectional curvatures. You can also do that and push these energies to the two-dimensional parts using this simple idea of distributing the energy around, and then you get a curvature which adds up to Gauss-Bonnet. But what happens is when you take this curvature at some point and attach it to the two-dimensional part, you use all the space around it and not only the two-dimensional part. Sectional curvature only uses the two-dimensional part. So that's the discrepancy. And when you look at Gauss-Bonnet Chern, that integrand is not necessarily positive from dimension 6 on. So dimension 4 it works, but in dimension 6 on it's no more necessarily positive. So what I try to do is just to build a curvature which is positive if the sectional curvature is positive, and see whether you can actually get close to the Euler characteristic like that. If it works, it should. There's still technical difficulties here. I'm not sure whether it actually works, but it was an attempt I tried in 2019. In the discrete, it's much easier to experiment. You take an even-dimensional manifold, produce index expectation curvature, and hope that you can actually build one which is positive. So there is much more flexibility in the discrete, and you can just change the weights in the probability space which you take. If you take a probability space of vector fields or probability space of functions, and then you get an average which of course always satisfies Gauss-Bonnet because of Fubini. Right? If you if this sums up to the Euler characteristic, also the expectation sums up to the Euler characteristic. It's just an average. So this is a very nice picture, this index expectation picture, which has a long tradition. It comes from Blaschke, then Chern, who has actually worked here on the Gauss-Bonnet Chern, then Banchoff, that's where I learned it from. He kind of looked at that, thought this was an important part, and in the discrete I use this a lot. So you can see curvature as an expectation of indices, and indices link with the indices which you have in the continuum. So in the continuum, you see what you can do is you just take a manifold and you take a small sphere and you compute this indices. So in this case, you take a small sphere, in this case of a hyperbolic point. If you have a hyperbolic point, negative curvature, so what happens is there's part of it is negative, a part of it is positive. So in this case, the Euler characteristic of that stable sphere part is 2. So it's 1 minus 2. The index is minus 1. But the indices here and here for maxima and minima are 1. But that works in general in arbitrary dimension. The two-dimensional case is just a particularly simple case to illustrate. So yeah, I'm mostly interested in sectional properties of the sectional curvature and to get a grip on what does it mean to have positive sectional curvature. Can you say something about the manifold? Can you produce the positive curvature manifolds which have positive sectional curvature? Can you maybe, understand why this is so difficult to get positive Euler characteristic, positive energy, if these sectional curvature energies are all positive? It's a vexing problem. I love this problem of Hopf, and that's it for today.